So, I already wished you, but I'll wish you again. May the 4th be with you. Yes, Star Wars, great series. Love it. Let's hold down for a second. A few items to think. Though the snow has melted, that could only mean one thing, and that means that summer is coming. I don't know if we'll have spring or not. Hopefully we have some sort of spring rather than snowy to summer. But I want you to think about this. So today is Wednesday, so we have Wednesday, Thursday, Friday, which we are starting a new unit. We will have a quiz on Monday. I'm just trying to give you this in advance. And then we have Tuesday, Wednesday, Thursday of next week, which we are teaching this unit. And then the Friday we will be doing a review. And then the 16th, so that is a week from this coming Monday, we will have our test on this unit. It's a smaller unit. And then 5:17, which is a Tuesday, review for finals. 5:18, which is a Wednesday, review for finals. 5:19, which is a Thursday, review for finals. 5:20, which is the Friday before final exams start. We will have our free response version of the final. Okay, your final's 2 parts. So free response, we are actually generating the answers. And then, this is second period, right? No? No. Okay.
This is 8th period. I'm done after this class.
Okay. So on 5:23, which is a Monday, you will have finals period 2, period 8, period 4. Not sure how that worked that way, but I'm just telling you how it did.
Wait. So 2 period.
So 284 will be on Monday, 5:23. And then on 5:24, we don't have this class, but you would have final exams in 3, 6, and 1. Again, not sure how they scheduled that, but they did. And then 5:25 is a Wednesday. We don't have school at all. We have graduation. 5:26, you have periods 7 and 5 finals only. And then 5:27, there is no school.
Wait, what?
And then we go back to school 5:28. We just start the whole year over.
Yes. Talk to me.
Yeah, one day off.
Yes.
No. No school. Sleeping.
So it's 284.
284, 361, 75. 75. So, yeah.
You said 284.
In that order, yeah.
We don't have
I'm sure you'll get more information.
So,
those are some things to think about. Now, let's go on the other end of the agenda. So some of you still need to make up tests or quizzes, which is great. So my schedule for today, I'm going to give you my schedule every day till the end of the year, each day unless it changes, okay? So today, I will be back in my office by about 11:10 for the rest of the day today. Still with me? Tomorrow, first period I'm over in that office, and then second period here, and then the rest of the day I'm over there. Okay? Friday, I am in my office, first period over here. We have this class. I have a meeting I'll be off campus from about 10 o'clock until about 12 o'clock. And then I'll be back in my office over there at about probably 12:15 on. Monday doesn't look like I have anything on my agenda. Tuesday next week, I don't have anything on my agenda. So first period over there and then over there. Wednesday, which is the 11th, a week from today, pretty open. Thursday next week, which is the 12th, I have a meeting right after this class until probably about 10 or 10:30. That'll be back in my office. The 13th, which is Friday next week. Oh, we got a Friday the 13th. Sweet, we should watch scary movies.
Yes.
Oh, yeah. It looks like I have a meeting off campus for the rest of the day. And then the 16th, so the 16th, the 17th, and 18th, 19th, and the 20th, which is our final normal week, it looks like I don't have anything on the schedule. So, did that give you enough insight of when you could make up stuff? Okay. Now, last case scenario though. That's my office number. You have my permission to put it in your cell phone. That way, if you're like, oh my gosh, I have a free couple of minutes, please call me just to verify so you don't always have to make the trek over there. Okay? Now, if you call me like in the morning and leave a message, one, leave your cell phone number and who it is. You go, hey, Mr. Strip, I want to see what's here with test. Bye. Who is this? I can see a cell phone number, but I don't know who it is. So I will try and call you back if I don't answer. Or if you leave on the message, hey, you said you'd be in today. I'll be in your office at about this time. I will make sure that I am there for you. But please, again, leave your cell phone number because just in case you're not there, I would be able to get a hold of you, okay? Sound good? We happy? Content? Casey, you got great hair, man. Yeah, buddy. He does. It's awesome. It's good stuff. All right, let's start this new unit. Ben's been bugging me about this for a while because his tutor says we should be doing it. Didn't realize tutors dictated math schedules, but
Yeah.
apparently it's changed now. But Ben's tutor has now dictated we start doing it. Sorry, Ben. Not trying to make Benny too much. Please don't cry yourself to sleep. I know most of you are going to be upset by this, but I don't plan on putting anything more into Schoology. I know most of you are going to weep uncontrollably, and that's okay. So I think it was a good experience for y'all.
Can we do it?
Huh?
What about the quizzes that we're going to be doing next week?
No, Schoology.
Oh, school. Oh. Okay.
So no more of the online quizzes.
Oh, all right.
Does that make sense?
Yes.
All right. Here we go. So this page up here should look similar to what you have in front of you. Okay, yours goes kind of sideways, mine doesn't. All right, let's go through and talk about this. So we talked about linear equations. Linear equations are straight lines. Talked about quadratics. Quadratics are parabolas. They're not straight line. Good. And then the exponential is where we're going to go to. So let's make this how we can generate this into usable terms. So on the linear equation, I have the function at x is equal to 3x plus 1. F at x means the same thing as y. Still with me? So we have functional notation. And then they say we want to know what the function at 1 is equal to. Okay? Blue should be good. All right. So function at -1 means right here, I'm going to plug 1 in. So I have 3 times 1 plus 1. What's 3 times 1? 3. And then 3 added to that. That's 1. So we get 4. Okay? Well, let's go over to the quadratic. So we have g at x, and g at x means the same thing as f at x, which means the same thing as y. Okay? I would like to know what g at 1 is. So I'm going to take 1 and I'm going to plug it in to x squared. So I plug a 1 in there, so I get 1 squared plus 2 times 1 minus 8. Still with me? What's 1 squared? Why am I doing 1 squared first? squared. Its order of operation says an exponent takes place before anything else. So I get 1 squared, which is 1, plus 2 times 1. 2 times 1 is 2, so 1 plus 2 is 3, and 3 subtracting 8 is -5. Okay, so I get -5 for an answer here. Cool? So now let's look at the exponential. Notice the x is the exponent. It's the raised power. Okay? H at x means the same thing as g at x, and g at x means the same thing as f at x, and f at x means the same thing as
Y.
Good. You still with me? So it's just a way of writing functional notation. Okay? So what I want to do on this one is I want to find h at 1. So I'm going to plug 1 in as my exponent. So 2 to the first power is what? 2. Get the gist of it a little bit? All right, let's start back with the linear. The linear, we have find f if function at x is equal to -5. So what am I going to do with the -5 on the linear? Plug it in for x. So that gives me 3 times -5 plus 1. 3 times -5 is? -15. -15, adding 1 to it, I get -14. Okay? So the quadratic looks like g at 0, I think. So I'm going to plug 0 in for my x squared. So I have 0 squared plus 2 times 0 minus 8. 0 squared? 0. Okay. 2 times 0? 0 added to the 0. 0. 0 minus 8. -8. Cool? All right. Now I want to find h at 0 for the exponential. So I'm going to plug 0 in for x. So I'm going to get 2 raised to the 0 power. Any ideas? 0 seems like the obvious one. 2 seems like it could be obvious. Positive 2, -2. Okay, yeah, maybe, I don't know. Everyone got a calculator out they can take a look at real quick? 2 raised to the 0 power. What do we got? 1. Okay, right. So we're not multiplying. So the reason for this, so if I have a number that is not 0 and it's raised to the 0 power, your answer becomes 1. Okay? And this has to do with something called logs and natural logs, which is a way to talk about really, really big numbers and condense them to a manageable thing, or really, really small numbers like decimals that are way far out. So scientific notation, in a sense, is what you're looking at, but you're using something called logarithms, which makes it a manageable number. Where you find logarithms in the real world, we don't really have them here, but earthquakes are measured on an energy on a Richter scale using a logarithmic equation. Okay? All right, so the next part says we want to fill in this table. Okay? So on the linear, I think we can do this. If I take -1 and plug it in for x, 3 times -1? -3. -3 plus 1. Okay? Plug 0 in. 3 times 0? 0 added to 1? 1. Plug 1 in. 3 times 1? 3. 3 plus 1? 3 times 2? 6 plus 1? 7. And let's graph it, sketch a graph. So at -1, -2, we're going to have a dot. At 0, 1, I have a dot. At 1, 4, I'm going to have a dot. and then at 2, 7. I'm going to have a dot. So all of our dots form a straight line if I can draw a straight line through it. Okay, so linear creates straight line. That should make sense. Make a quick graph. It's a quadratic, which is a parabola. So let's plug our values in. I think we can walk through it. Plugging -2 in. -2 squared. So -2 times -2 is 4. And then 4 plus 2 times -2. 2 times -2 is? 2 times -2 is -4. So 4 minus 4 is 0. And 0 minus 8 is? -8. Sweet. Okay. Now let's plug -1 in. -1 squared. That's -1 times -1, which is 1. And then 2 times -1 is -2. So 1 minus 2. 1 minus 2. -1. -1 minus 8. -9. Let's plug 0 in. 0 squared. 0. Plus 2 times 0. 0 plus 0. 0 minus 8. -8. Okay. Plug in 1 in. 1 squared. 1 plus 2 times 1. 2 times 1 is 2. 1 plus 2 is 3. 3 minus 8 is -5. So let's graph these. So I get -8, or -2, -8. And then I get -1, -9. And then I get 0, -8. And then 1, -5. 1, 2, 3. I'm barely able to see these. So this forms our parabola for the most part. So obviously that looks a lot different than a linear equation. It's not a straight line, it's a parabola. So now let's see if we can figure out how to do this exponential. Okay, you have a calculator by chance? And what I also want to do, I want to bring up come on, baby, hurry up. All right, so I'm gonna do this problem more on this board. Okay, and so if we fill in our table, so let's see if we can decipher this and figure out a pattern. So I'm just gonna kind of each one of these columns, I'm gonna kind of work out the problem under each one. Okay, so I get 2 raised to the -2. If you plug that into your calculator, what did you get? 2 raised to the -2 power. How much? 0.25. So this comes up with 0.25. Let's see. Hang on. Let's try this one more time. So let's take 2 and let's plug -1 in. What is 2 raised to the -1 power? 0.50 or 0.5. And then 2 to the 0 we discovered was equal to 1. And then 2 to the first power, 2. Okay. So I think I'm okay. I'm okay with how this and this work. I feel good about it. So let's think about the negative exponent thing. What does a negative exponent do to a numeric value if it's a fraction? Makes it a decimal. Good. Good observation. I like it. Okay, remember when we were doing tug of war? Like we had x to the third on top and x to the fifth on bottom. We say who wins top or bottom. You say, oh, bottom. And by how many? 2. Remember that? That's the same type of property that we're dealing with. So I have 2 to the -2 power. So let's think about this. If I had x to the -2 power, this doesn't like where it's at. So what does this want to do as far as being a fraction? Yeah, it's going to move that whole thing down. And if everything moves down, you keep a 1 there. Okay? Now, if I had like 8x to the negative third, what portion moves down? Does the 8 move down? Is the 8 raised to a negative exponent? No. So this would be the same thing as doing this. Okay? So let's go back a slide. This wants to move down. So this becomes 1 over 2 to the second. 2 to the second is what? 4. So 1/4. Is 1/4 the same thing as 0.25? Okay? Now the next one, this one, 2 to the negative 1, that means I want to do this, 2 to the first power. 2 to the first power is 2. 1 over 2 is 0.5. Now this one's fine. We've already deciphered this one and this one. But this is the reason why these become decimals. Okay, if I add 2 to the negative third power, that becomes 1 over 2 to the third. And 2 to the third is 8. So you get 1 over 8. And 1 over 8 is 0.125. Okay, so that's what's happening, why it becomes a decimal when we deal with this. So I have a few values. Do you have these written down? The 0.25, the 0.5, the 1. So I think we can kind of graph it now, if that's okay. Let's go back a board. Let's go to this. Okay, so at negative 2, we got what for a value? 0.25, thank you. And for negative 1, we got what for a value? 0.5, okay, thank you. And then at 0, we had 1. And then at 2 to the first, we had 2. All right, so let's see if we can just to make this graph. So at negative 2, I'm at 0.25, so barely above the line. And at negative 1, I'm at 0.5, so halfway up here. And at 0, I'm at 1. And at 1, I'm at 2. Let's get a little bit more information. If I took this out one more spot, if I plugged in 2, if I had 2 squared, what would I get? 4. So 2, 1, 2, 4. Looks like that. And if I had 2 to the third power, which is 2 times 2 times 2, what would I get? 8. So at 3, I get to 8. So this is what this looks like. Okay? So this particular line going this way is getting closer and closer and closer to the x-axis. It's not going to cross it over. Meaning, whatever negative number I plug into will get us a really small fraction. Our fraction won't mysteriously turn into a negative number. So you're getting very close to 0. 0, your x-axis is actually called an asymptote. I can't go over it. Now, as I continue to grow out this way, it's continuing to grow very rapidly upward. Okay? Now, things that are exponential growing things in life. If you had some sort of infection, let's say you got a sinus infection, your white blood cells like to fight infection. So your body realizes, oh, foreign body in my body, we need to produce white blood cells. What white blood cells go to work to battle this? So the infection is trying to grow exponentially, and your white blood cells are also growing exponentially. And you ever get that, sinus infection or something that just doesn't seem to want to go away? Your body is fighting like crazy. Your body is building cells exponentially while the infection is also building exponentially. And sometimes, if you're already been kind of sick, sometimes you can't fight off the infection fast enough because your white blood cells cannot fight and produce fast enough to do it. So we have an added advantage sometimes, and you can go to the doctor and you can get yourself medication, which all of a sudden changes the game plan for the infection. Okay, it doesn't necessarily produce more white blood cells. It basically gives your white blood cells a little steroid to say, hey, now we're fighting. So for every 1 white blood cell my body does, I'm going to take on 9 different infection cells. Kind of cool? So that's the long and short. That's where you would learn. That's where this stuff would take place. Exponential functions. Every year they offer a flu vaccine, and the Centers of Disease Control, the CDC, they take a prediction of, okay, what was last year's flu strain? What's the probability that these 3 or 4 flu strains might be the next ones that might kick up? CDC does research. They say, all right, these are the 3 or 4 that we think are going to be the active ones. So we're going to give you, if you do the nasal thing, we give you slightly live viruses, and your body builds antibodies to it exponentially. And so if you're come across the flu, somebody with the flu, or somebody sneezed, you have to walk through it, which I know sounds so good. But if you build antibodies to the flu, and you were exposed to that flu strain, you should not get the flu. If you happen to catch the flu, though, and you had the flu shot, a lot of times you are getting a lesser version of what the flu would have been because your body has already taken a defense against it. It just needs to battle it. So, I don't know the last time any of you had the actual flu was, and I'm not talking, you ate some bad food and you had, stomach bug, and they call it the stomach flu. That's not the flu. The flu knocks you out of the equation for 2 to 3 weeks. Aches, pains, headache, vomiting. You don't feel like good at all. There's no reason for you to be in school. Yeah.
We actually found out that just because I got sick so much when I was really little,
Yeah.
it's probably one of the only reasons why I survived the age.
Because you built up so many immunities to so many things.
I got really sick when I was little, and I was one of the only people in this really tiny town I was in at the time that caught H1N1.
Oh my gosh. So you have a nice immune system, which is always good. So you guys ever have, as you've gone through school, have you ever had like a brand spanking new teacher? Like they are fresh out of college. You're looking at them going, man, gosh, you look like a senior in high school.
Yes.
You know what I'm talking about? And then all of a sudden, they're like the first 2 weeks in, and they're gone for a day. And then they may be gone for another day. Teachers, when they first start out, they get sick so often. But the longer a teacher teaches, the less they actually miss school. It's not because they're like, oh, I can battle through this cold. The fortunate thing is being a teacher is all of you are a nice petri dish, and every kid at this campus is a nice petri dish of exposing us teachers to all kinds of wonderful things. Fortunately for me, this is year 21 coming to a close. I've been exposed to a whole lot of bad stuff. Now, do I get sick? Sure. Do I get as sick as I did when I was a kid? No. Do I get as sick as I did when I was a first or second year teacher? No. Why is that? My body built up immunity and antibodies to these things. My body developed these antibodies that are markers in my cells, in my body, that grew exponentially, those markers in my cells exponentially throughout my body to say, common cold, virus, T7. Just making that up. I might have been exposed to that particular virus in, 1995. So now if I'm exposed to it again, I more than likely won't get it. Or if I do, I get a lesser version of it. Now, viruses do indeed mutate. They mutate because the whole thing about any species, and viruses could technically be a species, it's a crystalline structure that is microscopic. I don't know if you know the difference in size of bacteria versus viruses. Okay, a bacteria would be the size of a football field. Still with me on this? So over there, Stutler Bowl. That could be like the size of a virus in the microscopic world. A virus is the size of a football on that football field. See, that's one of the reasons they're really tough to get. They are really small. Boy, do they wreak havoc. And they enjoy. Here's your biology lesson for the day, or anatomy lesson. So your smooth endoplasmic reticulum in your liver absorbs this. Smooth endoplasmic reticulum. The greatest word ever. Goes right across your liver, and your liver kind of says, hey, dude, what's up, virus? We got you covered, and we got the antibodies, and they whoop it. But then if they don't, they don't. All right. Hey, dude. All right, let's see if this is going to work. Is this going to allow me to move? All right. All right. They would like us to find the average rate of change between 0 and 1. The average rate of change between 0 and 1 is basically the slope. Remember, we used M? So, between 0 and 1, from here to here. From here to here. Y2 minus Y1, 4 minus 1. Over 1 minus 0. 4 minus 1 is 3. 1 minus 0. My average rate of change is 3 over 1. That's my slope of that particular line. Now, we can find the average rate of change for letter E as well. We can find the slope. This is actually a calculus concept in disguise that I'm throwing at you in Algebra 1. Okay? Find the average change between 0 and 1. Well, at 1, I was at -5 minus -8. Finding the slope, 1 minus 0. What is -5 minus -8? That's -5 plus 8, which is? 3. 3 over 1 is? Oh, sweet. Look. The slope of this rate of change between here and here is 3 over 1. The slope on the linear is also 3 over 1. Did we discover that the average rate of change between 0 and 1 is always 3? No. We got lucky. Okay, now let's find the average rate of change between 0 and 1. So I'm going to go 1 minus 0.5. And then 0 minus minus 1. 1 minus 0.5 is? Huh?
Your one doesn't show up.
Oh, thank you. That's minus 1. Thank you. All right. On top, 1 minus 0.5. 0.5. 0.5 over 1. Uh-oh. What's 0.5 over 1? So 0.5 over 1 is the same thing as 5 over 10. 5 over 10 reduces to?
0.5.
0.5. 0.5 is the same thing as?
1/2.
1/2. Good.
Hey.
Take a look. The average rate of change on this one changed. It changed to 1/2. Here it was 3 over 1. Here it was 3 over 1. But the exponential had a little bit different. Find the average rate of change between -1 and 0. So -1 and 0. Hey, let me ask you all this. Does the slope of a straight line change throughout the line? No, it's consistent. So what's the slope here? 3 over 1. Good. We don't even have to do the math. We get 3 over 1 here. Average rate of change here. -1 minus and 0. So I'm going to go -8 minus 9. -8. Come on, baby. Minus -9 over 0 minus minus 1. -8 minus minus 9. That's -8 plus 9. -8 plus 1. 1 over 1 is? Wait a minute. Rate of change here was 3 over 1. The average change here was 1. Okay, same thing here. Let's find the average rate of change from -1 to 0. So -1 to 0. So I'm going to go 1 minus 0.5 over 0 minus minus 1. So that's going to give me 0.5 over 1. 0.5 over 1 is still 1. Oh, it's 1/2 here. Cool. So average rate of change, you're just finding the slope. The slope, if you remember, the slope equation, if you remember, is this. Which, modified with functional notation, that's what it looks like. Almost done. We good? We happy still? And that particular average rate of change is at the bottom of your thing. We okay? Can I finish?
Yes.
Okay. No? Come on. All right. Use the graph to answer the questions 1 through 7. What was the highest temperature reached? Well, let's see. Our temperature is on the y-axis. What does it appear the highest temperature reached was? Is it that?
27.
Which is 27. 27 degrees Celsius. Okay. How fast was the temperature? Sorry. How fast was the temperature changing from 3 to 4 hours? So it went from, what's this change here? So at 3 hours, I was at 3 comma what? I don't know, 24? And at 4 hours, I was at what? 4 comma what? 25. So if you find the slope, 25 minus 24, 1. 4 minus 3. How fast was the temperature changing? It was changing 1 degree per hour. Okay? What was the average change from 1 to 5 hours? So at 1 hour, I was at what? 1 comma what? 25. And at 5 hours, I was at 5 comma what? 23. Okay? 23 minus 25. 23 minus 25. Negative 2. 5 minus 1. Negative 2 over 4 is negative half. So our temperature is decreasing by 1 degree for every 2 hours during that portion of our graph. Okay? That might happen. Over what interval was the temperature increasing the fastest? Ooh. So this is just a logical thought. If it's increasing, it's going up. Still with me? I'm looking for the steepest slope. So this slope, I'm looking for the steepest slope. This slope, and this slope, and this slope. These are all increasing slopes here. Where does it look to be the steepest?
7 to 8.
Here? Here to here?
8. Yup.
Yep. So between 7 to 8 is when it's going the fastest. When was the temperature decreasing? The temperature is decreasing here, and here, and here, and here, and here. Hey, what is the temperature doing here?
Staying the same.
Good, staying the same. I love it.
Yes.
And what was it decreasing? We can answer when it was decreasing with different rates. Okay? What was the average rate of change between 6 and 9 hours? So at 6 hours, we're at what? 6 hours, we're at what? 22. At 9 hours, I'm at what? 25. So we're going to do the slope. 25 minus 22. 25 minus 22. 3. Good try. 9 minus 6. 3 over 3 is? So for every increase of 1 degree, it's 1 hour of time. Or between every 1 hour is 1 degree. And what is happening between 9 and 10 hours? I think Gage said this. Same. So nothing. It's the same temperature. It's constant. Okay? Feel all right? Let's see. We will take care of those. So classify. Number 4 is linear. Number 5 is quadratic. Number 6 is exponential. And then I'm pretty sure you can work these out at a different time for just fun and laughter. Okay? Slaps and giggles and hoots and hollers. Oh, we are. All right. Your assignment for next time, which I will be marking off, so make sure you do it, is page 135, 136, which is worksheet number 1 on this unit. So if you need a picture of it, it's here in the basket. It will be marked off, so make sure you try the whole thing. You don't want to establish as many points as possible between now and the end, okay?